Let me prove this lemma quickly. If you have an element A in a group G that has order n, and you take some power of it, a to the power t, then it has order n divided by the GCD of n and t. So let's make some notation. Let me call d to be the GCD of these numbers n and t, and let me write n1 to be n divided by d. So n1 is this number up here. So I want to show that a to the power t has order n1. Meaning what? Meaning if I take the powers of positive powers of a to the power t, the first time that I'll see one of these elements to become identity is when k is n1. And the times when this would be identity is when k is n1, 2n1, 3n1, etc. So at least I have to first show that a to the power tn1 is identity. Let's compute that. A to the tn1 is a to the t to the power n divided by d. And n divided by d is an integer. You see, it's a natural number because d divides n. D is the greatest common divisor of n and t. So this is same as a to the power n to the power t over d, because that's the same number. And it looks like a fraction, but this is also an integer, you see, because d divides t. But then a to the power n is identity because a has order n, you see. So this is identity to the power t over d, and any integer power of identity is just identity again. That shows a to the tn1 is identity. Now suppose some power of it is identity. Suppose a to the kn1 is identity. And you want to show that a to the tk is identity. And you want to show that k is at least n1. In fact, we'll show that k is a multiple of n1. Some natural number k. The GCD can be written as a linear combination, right? So here's the trick. So note, recall, I can write d as a combination of n and t. So some number times t plus some number times n for some numbers u and v in integers. Let me compute for you a to the power t times d. Or rather, no. The k. A to the power d times k. Stay with me here for a little bit. You'll see what's going on in a bit. A to the power d times k is a to the power ut times k plus v and k. All this is in the exponent, and that's just because d is equal to this combination. That's same as a to the power tk u times a to the power n to the vk by our exponentiation laws on the left here. But a to the power tk is assumed to be identity, and a to the power n is also identity because a has order n, remember? So this is all powers of identity, which is identity. So what does that show? That shows that a to the power dk is identity. But we know that some power of a is identity when? When that exponent is a multiple of n, because a has order n. From last time, this shows the only powers of a, only positive powers of a that are identity are multiples of n. So since a has order n, we have that n divides dk. So n over d divides k. And this is an integer, by the way. It's called n1. So n1 divides k. So the smallest k for which a to the tk is going to be identity is n1. So n1 is the order. The other thing I wanted to do is talk a little bit about this additive notation. Here's a remark. We mentioned this briefly once before, but let me make it clear. Be an abelian group. Abelian means AB, that composing in either order gives you the same thing, written additively. Means what? Means that the group operation is written as a plus instead of a dot or a star, and the identity element is written as a 0 instead of a E. Okay. So for example, an example of that would be Z, where the group operation is plus and the identity is 0. So in there, what is the order? What is, first of all, these exponents? What are these exponents? You're taking a group element, like 3, and applying the group operation to itself. The operation is called plus. So when you apply the group operation to itself, you don't get 3 square. It's really 2 times 3. So what is being called a square here, in the additive notation, that becomes 2 times 3, etc. So what is called a to the n here, in the multiplicative notation up here, becomes n times 3. So then a to the n gets replaced by n times a. A inverse gets replaced by minus a, right? So what is the inverse of an element in a group? You have this element in the group, and you're looking for an element such that when you compose them together, you get the identity. The identity is called 0, and the composition is called here plus. So you're looking for an integer, which when you compose with 3, you get the identity. That thing is minus 3. It's not. So that's the standard name for it, so we stick to that notation. And then this law, for example, a to the m times a to the n is a to the m plus n, gets replaced by the law ma plus na equals m plus n times a. The order of an element in this language, the order of a is the smallest natural number n, such that n times a is 0, right? That's what replace a to the n is e in the additive notation. So for example, if you take 1 in z or 3 in z, this has order infinity. Because if you keep on adding 3 to itself, it never comes back to 0, which is the identity. But if you take the element, I don't know, 3 in z mod 15, then that has order 5, because if you do 3, 3 plus 3, 3 plus 3 plus 3, just composing that thing with itself, after 5 times you get 0, which is the identity. So this is 2 times 3, this is 3 times 3, and 5 times 3 is going to be 0. Yeah, so this has order 5. So we have to, when we are computing order, we have to remember which group operation we are talking about. Is it written as addition or is it written as a multiplication? And you have to make that adjustment. Let me talk a little bit about cyclic groups. They're extremely central. Let me at least give the definition. Now that we have talked about orders of an element, a group G, and let me switch to multiplicative notation. I mean, a cyclic group doesn't have to be multiplicatively written necessarily, but I have to written it somehow here, so I'm going to choose multiplicative notation. A group is called cyclic if there exists an element A such that every element of G has the form a to the n for some integer n. So every element can be written as some power, some integer power of a. So in terms, so if you write this list, that covers the whole group. There might be repetition, but that covers the whole group. So example would be z plus 0. This is additively written though. Generator 1 and minus 1. 2 is not a generator, because if you just take multiples of 2, you don't get all integers. But if you just take multiples of 1 or minus 1, you do get all integer. So it has at least one generator, so it's a cyclic group. This is an infinite cyclic group. If you take z mod n, that's a finite cyclic group. And again, 1 is a generator, but there are plenty of others. Actually, you can check that elements of z mod n star, the congruence classes that are relatively prime to n, these are all the generators. So for example, if you take z mod 6, 5 is a generator, because if you keep multiples of 5, you'll get 5, 10, 15, 20, 25, 30, and these are 5, 4, 3, 2, 1, 0, mod 6. So you get all of z mod 6. But if you start with, say, 3, then you just get 3, 6, 9, 12, etc. But these are just 3, 0, 3, 0 in z mod 6. So that doesn't give you everything. Yeah, so the generators of this z mod 6 are 1 and 5. We'll see soon that actually up to isomorphism, which we haven't defined what two groups are isomorphic means, which is really saying that their group theoretic nature is the same. They have the same group theoretic properties. That up to isomorphism, these are the only cyclic groups. So their structure is very clearly understood. We understand these groups fairly clearly. And given any element in any group, we'll see that it generates a cyclic group. If it has finite order, then it would generate one of these finite cyclic groups. If it has infinite order, it would generate a copy of Z. And that's why cyclic groups are centrally important. They show up everywhere. So anything else, like S3 is not cyclic. You can check the permutations of 3 letters, or D4. These are not cyclic groups. You can check rather easily because you know these groups, and there are only a few things. So you can see what every element generates, and you'll see that taking multiples of a single element, you don't get everything, ever. And let me explain the word cyclic here. So what we said, so for example, if you take Z mod 5, you know, one is a generator. You apply the group operation to itself, which is plus 1 here. So if you keep doing plus 1, you get 1 to 2 to 3 to 4 to 5, and then which is already 0. And then back to 1. So that explains the name finite cyclic group. In Z, it doesn't really cycle back, it just goes on forever, but we still call it a cyclic group. Okay. We'll talk about the cyclic groups in more detail later on in a little bit. But let me move on to subgroups.